Hello everyone and welcome to this presentation. I am B.SANKARI. My registration number is 17BEC0118. My class roll number is 04 and I belong to the slot A2 plus Da2. This is my digital assignment 2 presentation and my work is on the paper Study on Single Flex Quantum Floating Point Divider based on Goldsmith's algorithm. Moving on to the questions, the first one is explain how the selected paper is related to COA syllabus or curriculum. So in the past there have been a lot of addition and multiplication based on SFQ logic and a lot of studies have been executed on various hardware architectures, but in this paper the whole focus goes on to hardware algorithm for SFQ divider, which can be used for implementing SFQ based GPU. So the whole application of this paper mainly concerns on this algorithm, division algorithm, and how to implement it on the GPU based processors. There are two major hardware architecture approaches to implement the divider. One is the subtractive and other one is the multiplicative approach. The subtractive approach, which is quite similar to the manual division calculation, uses subtraction and shift operation to calculate quotient. The calculation time of this subtractive method is relatively slow because of the subtraction and shift sequence has to be repeated many times, at least the bit length of the dividend. So owing to the simplicity and the implementation, the subtractive method has been used widely in commercial microprocessors. Now, if we take the multiplicative approach, it basically uses multiplication to calculate quotient on the basis of mathematical algorithm. In this approach, the input dividend converges to the quotient practically by iterative multiplication. So the multiplication approach also has been implemented on various microprocessors like the IBM RS6000 and AMD K7 processor and all that. So here they have designed a bit serial SFQ divider that outputs 11-bit quotient. Result shows correct operation at the frequency of about 550 gigahertz and the bias margin of 80 to 125%. They also estimated the dependency of latency and number of Josephson junctions on accuracy of the output. So according to their estimation, about a double precision SFQ divider can be designed using 27,000 Josephson junction, which all can be implemented on a single chip just by using our current SFQ circuit fabrication technology. Logic circuit is thought to be applied to the next generation high performance computing HPC systems because of its very high efficiency. Now, if you take in the field of HPC, a general purpose computing on graphical processing unit is becoming a mainstream because of its very high performance in the calculation of power and energy efficiency. So in graphical processing unit, floating point algorithm operation plays an important role compared to a general purpose processor. So when you compare even all the four arithmetic operations, division is one of the most complicated and it requires the longest calculation time. In this algorithm, it is reported that the floating point division accounts for approximately 40% of the total time. And although the division occupies like about only 3% of the total instruction, it does take a lot of time for division to take place. So that is about the paper. Moving on to the next question. Draw the existing architecture discussed in the paper. So this was the architecture that was discussed in the paper, and I do this with the help of a tool called Da2 It is a very versatile and easy to use software, and it does take a lot of time in the beginning, but with enough practice, I think anybody can draw a circuit like this in a matter of few minutes. So moving to the next question. Draw the tabulated results and graph. So as I told in the beginning that they estimated a relationship between accuracy of the quotient, which is basically the output, on latency and number of Josephson circuits to get a double precision divider we have to have more number of Josephson circuit. We can get max accuracy for about 27,000 Josephson circuit. And here, with the increase in latency, the accuracy of the quotient increases. Moving on to the next question. Draw the proposed architecture discussed in the paper. So this was the proposed architecture that was discussed in the paper, and I drew this with the help of this tool called Da2 A2. Going to the next question. Draw the transistor level internal diagram using electronic schematic capture. So this is the transition level internal diagram. This flowchart perfectly explains how the algorithm takes place, and I drew this with the help of Draw.io software. The sixth question is, compare the proposed architecture with existing architecture in your reference book. So first let us understand this architecture and how it works. This is Goldsmith architecture. Here Z is the dividend, D is the divisor, and Q is the quotient. And all of these are represented as Z as this, D as this, and Q as this. Q is Z divided by D. And there are just three steps in this algorithm. First step is D naught is assigned as DF, X naught is assigned as DF, and Z naught is assigned as ZF, and X naught is assigned as 1 by D. So starting the for loop for I equal to 0 to K, we are going to get Zi as Zi minus 1 into Xi, Di as Di minus 1 into Xi minus 1, and Xi as 2 minus Di, and we end this after the loop runs for K times, and we return Zi. So this is how the algorithm works. After seeing the algorithm, one can understand that the two calculation represented by and can be performed by repeated simple multiplication. Moreover, multiplication represented can be achieved independently. So we can completely ignore the data hazard on each of the multiplication branch. And this can be effectively done by introducing pipeline. Goldsmith's division algorithm with iteration of simple multiplication is suitable for SFQ circuit that has latching function and logic gates and implementation of pipeline without pipeline registers. So going on to the seventh question, list the advantage of proposed design over existing design. So advantages of SFQ divider is that it has high speed, low power, and it is the best for determining the power and energy efficiency, and it has high performance. It supports high performance computing. It has high energy efficiency, quicker output in terms of response time, and efficiency to perform all four operations. So let's move on to list eighth question. List the merits and demerits of proposed and existing technique or hardware. So advantage is that using a 4-bit SFQ divider is composed of one pipeline multiplier, and when the bit length of divider and dividend are 4, accuracy of 2 power minus 11 can be obtained by iterating multiplication by 3 cycles. And for this whole, the estimated latency and number of Josephson circuit required are very less. One more is that a whole double precision divider can be implemented by using 26,518 Josephson circuit using just this architecture, and it can be implemented on a single chip using the current SFQ circuit fabrication technology. Moreover, data hazard does not occur due to independent multiplication branch, and this multiplication can be very efficiently performed by using or introducing pipelining. Moving on to the next question. List the application of proposed design. Considering this, this is one of the very few papers that found an algorithm, SFQ algorithm for division using Goldsmith's algorithm. It can be used for since it is a very small circuit area and multiplier, it's completely multiplier based hardware architecture. This divider can be applied to build an SFQ graphical processing unit, and it can also be used to implement GPU processors. Going to the next question. Draw the flowchart or algorithm or transistor level circuit proposed in the design. So this is the flowchart that was proposed in the design, and I drew this with the help of Da2 A2. And I have taken some notes from the paper that I used. So this is it. Thank you very much for listening to me. Have a good day.